So I'm going to go through and kind of look at the first steps that are here to get an idea of what's happening. So we get to see acceleration, which is really pretty nice. So we see a pretty good lean forward, and then it comes a bit more erect, like you should. So that's typically how you would start. The arm motion is pretty good. It also swings forward a little bit there. And then no sooner does it kind of get up the top speed, and then it already has to slow down. So this looks more like a basketball drill than it does running, because the basketball players have to do this and turns around pretty quick and gets started upright again. Okay. And then unfortunately goes out of frame. Had to talk to the cameraman about that. So we could kind of see it going on. But we'll see, like right there, that is pretty good time of flight. I mean, we have like multiple frames of it actually in the air. So and that's pretty good back kick and everything else that's going on there. And it looks really kind of relaxed doing that movement. So that's not bad. Now, as far as the foot, I know they have a compliant toe box because I held it in my hand. As a matter of fact, there is a picture of me standing right there with figure three. So I'm familiar with that, the couch and everything there. The and I think what's happened is they probably a couple of things. First, they have a nice shaped toe box there that's able to roll off the shoe. And anyone that has like a pair of basketball sneakers or something like that has them roll off, you probably know you do that and your toes almost never flex. It's almost like the shoe is doing all the work for you. And you put that in there and you get much closer to my original guess, which is like about 4.5 meters. So from start to finish line is 4.5 meters. And the time stamps that I was counting the frames and stuff like that, and so long as I did that calculation right, means we're about 2.68 meters per second, well above the 1.2 that we'd like to see in a factory, and very close to 10 kilometers per hour. Oh, hey Mara, how you doing today?
I'm doing well.
Long time no see. I mean, it's like we're planning kind of like a weekly podcast here, an episode, and then once again, news kind of jumps ahead of us. So on yesterday's podcast, we went over the human bot, the humanoid bot, I should say, out of the UK, and some of the interesting mechanical choices that they made there. And I was about to kind of complain that, well, their bot's really slow, and then really like no one from North America has been, except for Boston Dynamics, has shown their bot having like a human like walking speed or being able to run or something like that. And then of course, lo and behold, Tesla comes out and reveals their bot walking along in a pretty good clip. And I took a couple of stabs on X, and I was like, I'm constantly being wrong of what the speed is, and I think we'll have it right now. So now they've had like 48 hours to go through and think about it. I think we're going to do it, and we're going to work together on this. So I have to make sure I kind of get it right. Um, but not to be outdone, Figure then kind of clapped back and said that, yeah, Figure 3 is running as well. And they showed that. And both of them are great, along with what we have with Boston Dynamics.
By
So,
the way,
yeah,
do
yeah.
you, do you think Figure did this because this let it the run, or I don't think the timing seems very close. But
Well, I'm sure it's been doing it for a while. It's not like they just said yesterday we've got to go ahead. It's there. It was just more of a decision of when do we go ahead and show what we have. So I'm assuming Tesla may have been working on it also for a while, and whether that was like just what they just got it for the first time, or they've been doing that, and then it was like you may be capable enough that, yeah, let's go ahead and show something. But let's say everyone's breathing a little bit better as a result, because these bots were just so slow. It's like, when are they going to be as fast as everything that we're seeing out of China? So why is China having no problem, and then like in the West everyone can get their bots to walk, but that's it, nothing more. So we can see that it's some capabilities are getting unlocked and we can do it. And we've been told that, yeah, the bots can do this, that they say there's enough headroom in there and stuff. And all of their simulations are showing it's like, okay, but simulations can show a lot of things. And then when you try to deploy it in reality, it turns out you have some sort of difficulty. So it's really nice to be able to see that. Now, Figure 2 may have been able to go a little bit faster. I don't know. They potentially could have unlocked it. It looks like they didn't really bother to want to unlock it for Figure 2 because all the energy was going into Figure 3. So Figure 3 really wasn't up to, let's say, full capability until I think maybe September or something like that. Or October is when we get the unveil on that. So since then, they've been able to take it and doing more and more things. And so, now we're seeing that, hey, it can run and it can run pretty well. So I'm going to kind of jump back and forth on a few things here, but um, let's go ahead and just see what we got here. Is that the first thing is I'm just going to share this screen here, and this is what we saw. And I'm trying to remember if this is just this. I probably don't even have the running in here. So what I'm going to do is this is the screen that everyone's been looking at. Oh yes, I do. It's going to actually show Optimus running through here. So this is what everyone was rather excited about the other day. I've compress this a little bit, so just the running parts. It's like a 4-second clip in which only about 2 seconds of it are actually running. And the big question everyone has is at the top, I said it was like, new PR in the lab. And for those who aren't familiar with running, PR is basically running slang for personal record. And so that means Optimus has hit a new speed record for itself. But unfortunately, we don't know what it is. And this is the complaint that I've had, is that usually we'll see these updates and they'll say something like 30% faster or 10% lighter. It's like, oh, wow, it's great. But 10% lighter than what? 30% faster than what? And even though everyone's website will say, it can do 3 miles an hour or 5 miles per hour, that is all what they'd like to achieve. They designed it for that, but doesn't mean they've achieved it. And usually when they've been showing the first walking videos of many of the bots, they were nowhere near what their supposed design specs were. And we have to reverse engineer to figure out what the speed is. And so a lot of times, 30% faster than 1 mile per hour is still not very fast. And as I keep on saying, the benchmark is for factory usage 1.2 meters per second, which is about 2.5 miles per hour. And until now, we have not seen Optimus go much above 1 mile per hour. I think about 1.25. So very nice walks. You look at it, just like the Xipeng, the catwalk. It's like you look at it and go, wow, it just looks so human-like. It says, yeah, but not as fast as a human. So a very casual walk, you would like to see like a more normal pace. And so we haven't seen a normal pace, let alone a brisk pace. But now we're seeing, oh, okay, unlock some speed here. So if we want to determine how fast this is, what do we have to do? do, do you know what the steps are involved to calculate speed?
Hmm. We need distance and the time.
You need distance at the time. Exactly. So the definition of speed is distance divided by time. So we've got to measure both of those things. And in order to come up with like the time, we have to come up with a start line and a finish line. And then the other thing we have to do is, find out what that, and then measure the crossing of those times of the start and the finish line. And then we have to know the distance between the start and the finish line. And they may seem all easy, but since we don't really have any good references in here or anything to kind of tell us to calibrate it, it gets a bit tough. The time is fairly easy. So if we determine that there's a point in time or location that we want to start from there and go to something else, we can get it just by counting the frame rates in here. So when you download these things, they'll download, 30 frames per second or 60 frames per second. I believe when I finally get this downloaded correctly versus screen capture, stuff like that, there's a 60 frames per second version. So you can go through and see every one of them. And from that, be able to get a very accurate time splits of from one location to another. Now, when we measure the running speed, you do not want to measure the foot because the foot is momentarily stationary a lot of times. And so you will get to see on what the actual speed is if you use that as some sort of reference. So the reference is usually like the chest or the center of gravity or something like that. This is why track and field, the person that crosses the finish line, it's always about the chest. It's not about the arm. It's not about the leg kicking out. They always go for that. That's where the finish tape is supposed to be. So we want to kind of do the same thing to make sure we're actually able to measure the time accurately. So I've gone through this and I've been able to come up with a fairly accurate time. The problem is getting the distance that it traveled. And I overthought the problem. Okay. So we can kind of go through here and see like, what do I mean by I overthought the whole thing? So we'll come back to this slide here just in a second. First of all, we can see that Optimus is running. And so the running that we can see there is technically a run because both feet are off the ground at the same time. So walking is one foot is always in contact with the ground. But you always have to have one. And if you're in a walking race, if both are off the ground, you're disqualified immediately. So technically, it is a run. And this is what's known as the flight phase. I prefer the ballistic phase because that's technically more correct, but this is biomechanics refer to that as the flight phase of running. So uh, now, you may have noticed that you have this sort of happening with the toe box. So, it's great to see that Optimus does have a toe box because that's, I think, very important to having a good running gait. And when anyone watches the video going through there, you'll notice that. And you may notice, like for a frame there, this rather interesting effect happens of the toe box. And there's like a slight flaw in the design of the toe box that we'll get an idea right here of what's going on. And this probably looks like a familiar simulation because we did this last spring when we were first talking about this. Everyone was seeing the toe box that had actually been there for a couple of years, but no one really noticed it. So it is an articulated, not an actuated toe box. It's very difficult to make them actuated. You have to put, more stuff down there to be able to do it. So you have a compliant mechanism that will basically push it back in the spring. But the problem that we see here is that this gap opens up. That's how they designed it at Tesla, because you can see the hinge is up high, that air is going to open up. And for some reason, they decided to make the sole into two pieces rather than a single piece that would somehow stretch or slide over it to keep that covered. Now, that's problematic for a couple of reasons. That if you're running outdoors, you're going to catch pebbles and other debris in there that will actually prevent the toe box from closing, which is something that you would not want to have. But the other thing is it causes this. And this is being caused in the foot drag back. So when you're trying to propel yourself forward, of course, there's a possibility that your toe box could slip a little bit depending on what the grip is there. And if that happens, it's going to catch that lower edge and it's going to have a little force which will push back on it right there. So basically, as velocity goes back, you get a little bit of forward push there. That's going to create that yellow torque in the counterclockwise direction, which is going to open that up. That's one way, and that's something that we actually saw in the dancing videos that came out in May, where Optimus was jumping up and down, stuff like that. And everyone's noticing this, like, why is that weird toe flap that's going on? And why was it, look, it's got a toe box now. I was like, no, it's always had a toe box, but it was flapping up. And that could also be accomplished in other ways, and that is it just comes down and smushes it open by putting too much pressure right down on the opening when it begins to open up. And I believe that's more likely what happened, is that when that kind of started to deflect like that, it then pushed down because it was wanting to open up, and then a bit more force came down, went ahead and pushed it. And we can sort of see that from the sequence that I captured of Optimus running. So here we can see the frame with the heel strike. And then this is the next frame after that, where we see the foot is flat and we see it's flat again. And you'll see the toe box stays pretty much where it is. Now, in some frames, you'll look at it and you'll just see the toe box jiggle a little bit in there, but it doesn't go very much. A lot of time, and that's just the reaction force from the impact. It's down there. It's just going to cause that, but it comes down there pretty quickly. So that's not what's causing it. What's causing it is on the toe off, as we can see here. Pretty much all the force is going right down there, and it just causes that to momentarily open up, and then eventually it hits its limit of travel probably right there, and it's able to kind of keep it in there, and then the spring mechanism will return it. Now the big question is, like, what should the compliance be on the spring? Now, it looks like they may have one that's pretty loose and doesn't have a lot. Um, in some cases, is that over articulation of what you want to have with toe box? What do you want to have? So you can probably tune these things to be much stiffer. So you could have a toe box that may do very little, but may be able to catch a little bit, and also some design changes that they could potentially do in there. So now that's kind of analyzing a little bit of what's going on. There's many other things we can look in the gait and how the arm motion, stuff like that is. That's all kind of interesting that we'll try to get back into. But if we go ahead and take a look on the next slide here, what I kind of talked about is this idea of putting up a start and finish leg. So I get the tapes, the start and finish tape, and this is where I overthought the whole thing. As I said, wait a minute, I know how tall the optimi are in the back. I can probably measure the distance from here to here. And if I draw these lines in the perspective right, then I know what it is. And what I think I did is I tricked myself into thinking that this was the right perspective lines. I think the perspective probably is a lot steeper than that. And this is where I kind of overthought it. But anyway, so what I did is I said, you take something like that, you put them enough along there and you calculate it. And the first time I calculated it, I had a data entry and I said it's about 4 meters. And then from that, I get the calculations did it. And then someone pointed out, so that distance doesn't look right. And I went back and said, oh, I should have done the mental calculation in my head rather than trusting a calculator. And I would have seen that it's definitely more than 4. And then I would have come up with a distance that was more like 6.5. Um, that's the correct distance back there. It's not the right distance up front. So the real smell test should have been, does it look like 6 meters up front? Um, and part of my original one, why I didn't recheck the calculation, is it more or less the confirmation bias is the number that came out was about what my intuition said. It's like, it's going to be around 5 miles per hour. Something like that wasn't my expectations. It was like, oh, it's 5 miles per hour, slam dunk, done. And then I make the mistake of like the pendulum swinging too far the other way and then going ahead and trying to redo the calculation, thinking it was 6.5. And that got me up to a really high number, like 8.5, which I said, that is not right. It's like, there's just something wrong about that. There's got to be some sort of error. I was wondering if I was getting the timestamps right, looking at the timestamps, all that stuff, because come on, it's simple. Either the distance is wrong or the time is wrong, maybe both. Um, and John Gibbs and I kind of went back and forth on it, and he got a little bit of help from Gemini and others. And Gemini used a slightly different approach, and it was thinking around 5.8 miles per hour, which I will eventually get into meters and everything else there. But definitely saying that 8.5, this did seem right to me. So um, this is the false distance that I kind of came up with based on that. But um, the actual number right now, so I redid the calculation, and you see we do have an Optimus in the foreground, which I should have said that's obvious. Just pick that Optimus and see how many of them go across the screen. And it turns out it's not like 3 3/4 like I thought back there. It's actually like 2.6. And you put that in there and you get much closer to my original guess, which is like about 4.5 meters. So from start to finish line is 4.5 meters. And the timestamps that I was counting the frames and stuff like that, and so long as I did that calculation right, means we're about 2.68 meters per second, well above the 1.2 that we'd like to see in a factory, and very close to 10 kilometers per hour. And I get this is almost exactly 6 miles per hour. So for those who like freedom units versus metric, those are the numbers there. And that's a pretty good clip. And that makes sense because we agree Optimus is not walking, right? Now the question is Optimus jogging or running? What does your intuition say?
I think it was jogging, not running.
Yeah, yeah. And the thing is, now there's no strict definition of jogging except that it can't be walking. And we know that not walking means you have a flight phase. And Optimus had the slightest of flight phases. I mean, it's like you could find one frame where both of them are just barely off the ground. And it's like, okay, it's flight. And that means it's in a jog phase probably at that point. And in jog, usually we'll say somewhere between 4 and 6 miles per hour. And when you start to get north of 6 miles per hour, then it's like it's more of a run.
Oh.
And so it's like, oh, okay, just based on our intuition, that's why we were kind of feeling it was like 5, maybe a little bit faster than 5. And 6 seems reasonable, much more reasonable than 8.4, because 8.5 seems like a fairly hard sprint. It would be for those who are used to like running a 10K race, it's about a 43-minute 10K race at that. This is a lot better. This is about an hour. A little bit more, 6 miles, because a 10K is 6.2 miles. So, okay, right about an hour mark for a 10K. And that looks right. So anyone that's used to seeing weekend joggers and stuff like that, it's like, okay, I can accept that. is that right? So hopefully that kind of ends like this is no longer a hot take. All my hot takes were wrong. Now, after kind of going through it and then and this is why you should always do it. Second, never trust a calculator. Always do a hand calculation or calculation in your head to say, is this order of magnitude right? And then you did the data entry right. And the other again is it has to pass the spell test. And it was like nagging me. And then it's because I overcomplicated. It's like perspective was like just the wrong way to do it. Just go to the foreground and it'll be a little bit. Doesn't mean this is exactly the number, but it means we're probably within 10% of what the actual number is. So from there, we had some other things that kind of happened is that this is not the first North American bot that can run. It's the second. And then today we got another entry, which is the third one, which is coming from figure. And I haven't had time to like actually make the full clip. So what I'm going to attempt to do here, let's see if how well this is going to work out for me. Um, is we're going to try to go to DaVinci and see whether we can run that at the same time. And there's my stop share button there for a second. So we'll go share somewhere else right now, and then we will go ahead and take a look. If I can go ahead and get that, and yeah, okay. So I'll make sure I'm set up for the next one here, and then we'll go ahead and see if I can share an entire window right now or screen. Actually, I think window. I think I can do this window, and let's see how this works. Okay, so I think we can see this. This is DaVinci Resolve right now. And so this is the Optimus video where we can go through frame by frame. And you see like they burn the first 2 seconds before we see anything. And we can see Optimus coming through here. And so we can see, oh yeah, so you see how the foot is kind of collapsed underneath there a little bit. And it's kind of brief, comes around, some toe off. It's like just barely airborne there. So it's like, okay. Did you get, because right there, that foot's up in the air and then that one is down there, but I'm sure there's like a frame in between. We can see what looks like a pretty good pause. You know, we can see it kind of coming off here. Overall, its running is pretty good. A little bit of lean forward, and the arm motion is actually very good. If you just kind of look right in there, you see how the arm kind of swings in front of the body? That's pretty good. That's really kind of a natural running gait. And the question is that something? Oh, and I think if we look right, oh yeah, you can see right there the crease that opens up in the foot. Okay, and that looks fairly natural running style. And the question is that something that was learned behavior, or is that something that was kind of put in from some sort of human priors? And we're going to talk about this a little bit because there's a bit of a debate about how these all these running gaits are being trained right now. Is what was the way. So we can see that again. It doesn't look robotic in the arm motion, and again, I joke it doesn't look like Tom Cruise, where Tom Cruise has like the straight arm pumping back type of thing, which looks great in an action flick, but is actually the worst way to run. Like your legs perfectly, you actually need to have a little bit of movement back and forth, and that's what you're seeing here. So that's typically how a jogger would do it. And whether it's learned behavior would be really interesting. That if it determined that is the way that's the most energy efficient, or is something in the training set forcing it to run like a human so it looks more human. Um, and that I think that's something I'd love to know the answer to. The other thing I think we all love the answer to is why can't any of these companies tell us how fast that is? They'll all say real time. It's one axis. It's not sped up, but then we have to go through and do the forensics. And as you can see, I'm sometimes like Detective Clouseau out there on the forensics, getting everything wrong. All right, so here is the clapback from Figure. This is right in Figure HQ, right inside the office, right in the front lobby. And here is Figure 3, and I will run it real time, and then we'll go through. Okay, so what'd you think of that?
I feel like the chest is leaning forward. It's just a very different way of it's funny.
It's slightly different. Yeah, it's slightly different. Now, the other difference between these two videos is that Figure downloaded the sound. Tesla, there was no sound. I mean, I was like, I wanted this here. So, oh, what are the footsteps like? So we can actually hear. So I'm going to go through and kind of look at the first steps that are here to get an idea of what's happening. So we get to see acceleration, which is really pretty nice. So we see a pretty good lean forward, and then it comes a bit more erect, like you should. So that's typically how you would start. The arm motion is pretty good. It also swings forward a little bit there. And then no sooner does it kind of get up the top speed, and then it already has to slow down. So this looks more like a basketball drill than it does running, because the basketball players have to do this, and turns around pretty quick and gets started up right again. Okay. And then unfortunately goes out of frame. I have to talk to the cameraman about that. So we can kind of see it going on. But we'll see like right there that is pretty good time of flight. I mean, we have like multiple frames of it actually in the air. So and that's pretty good back kick and everything else that's going on there. And it looks really kind of relaxed doing that movement. So that's not bad. Now, as far as the foot, I know they have a compliant toe box because I held it in my hand. As a matter of fact, there is a picture of me standing right there with figure three. So I'm familiar with that, um, the couch and everything there. The and I think what's happening is they probably a couple of things. First, they have a nice shaped toe box there that's able to roll off the shoe. And anyone that has like a pair of basketball sneakers or something like that that has them roll off, you probably know you do that and your toes almost never flex. It's almost like the shoe is doing all the work for you. But I think there might be a small amount of flex in there. Definitely not as much as we're seeing in Optimus, or it could be that the compliance is so strong, it really doesn't do very much because it is, you can see there's still good contact. Whereas a lot of the other robotic feet we see out there are so flat, they go from full contact to just like right on the toes. So there is a little bit there for the push off. So it's definitely more clear in Optimus and not so much here. Now, the big question is how fast is it going? How fast do you think it's going?
I think it's more faster than the Tesla bot. It seems to me
It,
more
it,
faster.
yeah, I mean, it's kind of deceptive to tell what it is because it doesn't seem like the bot ever really gets up to full tilt. It seems like it's accelerating and then slowing down. It's almost like you got to go from this line to the other line and
Mm.
then stop really quickly. And it almost seems like it's in a break very early. So if I run it at normal speed right now, it's like, man, that was like really, so I almost wonder, it's like, oh, what are we showing? Are we showing, maybe 5 miles per hour or something like that there? It was kind of hard to tell. So I had to do the same thing that we all do. And that is, unfortunately, we didn't have that nice long picture that we do with the Tesla picture. So the background keeps changing. It's really hard to measure some length. But fortunately, we have these lines.
Ah, okay, okay.
Okay, so we have the line there and we have the line there. Now the thing is, what's the distance between the lines? Or what are we going to use to kind of measure what that distance is? And again, I decided I am going to do the background trick this time because I have proper lines of perspective. And you see what's in the background? Mhm. Furniture. And so we have the couch, and the question is like, how long is this length here? And it's kind of hard because everyone's sectional will be a little bit different. But if we know what the length of one of these things, we can basically, we've got one here, almost one. Okay. And then you could call that one two. And then I'll ignore that one there, call that three, and then call that one four, even though it goes over. So basically, I'll say that there's four sections in there because I didn't allow this one. I'm ignoring that one. And I mean, it looks like two people can comfortably sit on that. I think the real trick was looking at the height. So I was able to get a pretty good idea. You, you don't want a couch to be too high or people's feet are dangling off in the air, right? So there's kind of a standard height that you would have from a couch. And based on that, I could figure out what the actual width of the couch was. And then once I knew the width of the couch, again, it was just taking four times that width and you come up with a distance. And the distance I came up with was like right around 6 meters. So that means like each of these is about a meter and a half, something like that is what the final version is. So the distance between there is 6 meters. And it turns out 6 meters is almost exactly 20 feet. And so because that was like such a nice round number, 20 feet in American construction, more than likely that's something that they would use. They would measure off something like 20 feet in there. So that's like another reason why I have like certain high confidence that I get the distance right this time. Then I went through and I got the times, and somewhere I posted that. I don't think I put it up here in our in the PowerPoint, but I came up with it being right around 7 miles per hour. And so what I should probably do is actually look at my own post that I put out there, and we can take a look at what I said the time was. And
Maybe share it here. Can you share the book?
yes, yes, is exactly what I'm going to do right now. Is we're going to go ahead and get that, and we'll be able to share that. So I'm going to be live editing a PowerPoint. So this isn't this exciting. Make it a little bit easier. Make it a little bit easier for us to take a look at. So I'll go ahead and get that, and then I'm just going to go ahead and stick it on in here to my PowerPoint, and then it's a little bit easier for me to get this thing to display. Okay, so all right, so let's go ahead and so is there anything else you want to see in DaVinci Resolve before I kind of take that out? So the playing around. I don't know if there's any other interesting aspects of the movement that's what's going on here. Oh, that was interesting. I think it slipped a little bit, probably because it still had a certain amount of momentum. You could see it skated just a bit, turns fairly quick, and then just starts right back up. Yeah, I mean, he looks like the guy that's like not taking the basketball sprint drills seriously. In a way, he looks kind of lackadaisical there, in my opinion. But all right, so we'll go ahead and we'll start to get the sharing here again. At first, I actually need to have something worth sharing, so we'll go from there. And I've popped everything around here to make my life difficult. Okay, so we go ahead and find the right screen here, and we can go ahead and take a look at that. So here's my calculation. Okay, so 3.2 meters per second is basically what I came up with. Um, so between the lines, including acceleration, deceleration. So the peak could be faster. So that's actually pretty impressive average speed. And so that would be around 11 kilometers per hour, or 7 miles per hour. So that's something else. It's like zip, zip, up there and down to be able to see both of those things. It's a shame we didn't get to see what the Tesla bot looks like starting and stopping. We only saw it kind of going through doing what usually referred to as the flying start, which you do like in a relay. So it'd be interesting to see how quickly Optimus is able to come up and what's like be able to slow down. So figures like showing coming across, stopping, turning around pretty quickly, and coming back. I think that's pretty impressive. Um, so that's kind of the status of the speed. So it makes sense because again, if you look at the flight phase that's there, the flight phase is so more pronounced than what you're seeing in Optimus that you would expect it would probably be a little bit faster than what was going on there. So I would say it probably is. So my absolute numbers could be completely wrong, but I think relative, it might be about the same ratio between the two on the kind of speed that we're going there. Also, you can see the lean forward is a little bit more someone that is aggressively sprinting and moving fast, whereas Optimus is more like in the jogger mode of keeping the torso up a little bit further. And remember, walking and running is a controlled fall. So if you're running really fast, you literally want to be falling forward more, which is a lot of the reasons why you'll be coming down a little bit more, and then you just got to get your leg speed out there. The other advantage that Figure 3 has over Optimus is the hip height. So Optimus has a very low hip because of the actuation strategy. The ARF actuation strategy puts the flexure down very low. It's not actually coincidental with the other joints. So that there means that it's losing a little bit on its stride because its leg length is like almost about maybe 4 or 6 inches shorter than everyone else's as a result of that. So it needs more leg speed to be able to make up for the fact that it can't have as long of a stride. And you can see that a little bit when you see Figure really getting along there, that its back kick is really well out there and looks very, very good. So that's quite impressive to see that. So that's the speed. Not bad. Not bad. Now, I'm not sure I mean, we have ideas of how fast some of the Chinese bots are because they had the Olympiad and they were running what they would call records for like the 1500 and the 400 and stuff like that. I'll have to go back and actually find out what that is in miles per hour. I think Cassie had, how fast did Cassie hit maybe 11 miles per hour? Because Cassie was just a leg only biped. And it did, was it like a 20-second 100 meter or something like that? Which I'll have to, but I think its top speed might have been somewhere around there. And there may be a few that have kind of hit that. So there are some that are going faster than this. And but to be fair, I think we have to think about is that it's one thing if you design your humanoid just for running. They're designed to do useful work. So if you're not having to carry around the excess mass of actually working hands, does it count? So you should have some degree of functionality in there because Figure and Optimus could go faster if they just said, let's take that forearm out. Let's get rid of that forearm mass and put mannequin hands out there and we might be able to get a little bit more speed so we don't have to worry about that. So there's that. And then okay, I'm clicking the button in the wrong place. Is I want to actually get to I think there's another slide. This slide here. So here we go. The North American humanoids. They're running finally. So credit to Boston Dynamics. They showed this way back in the spring. So far back, I can't remember exactly when it was. But this was taking some motion capture, if you remember. It was doing a bunch of other gymnastics, and it actually had a short run phase in there. And I went back to that, grabbed one short clip in it just because I wanted to see, did it have a flight phase? And it does. So it clearly has a flight phase. I'm not quite sure what the speed is because I made that mistake so many times. I'm afraid I got called out on that one. He is the shorter of the bunch. He's like right at 5 feet. Figure is like 5'6", and I think Optimus is like 5'8". Um, but when Boston Dynamics came out with it, the very first time in the reveal, we could already see it. It had a fairly good walk. I think it was walking close to 1.2 meters when it went on out there. One thing we can see is it has very flat feet, and I don't think it has a toe box. So that's one disadvantage. The other thing we know is that when we hear this thing running with a sound, it is crying. It's definitely making the noise. Figure sounds a little bit lighter. I mean, you could still hear it. It almost sounds like someone on the basketball court. The kind of same kind of the sound on there. Optimus, we have no idea. I don't think Optimus is going to sound metallic because it does have some sort of soft cushion there. It's disappointing that they didn't have the sound on. Maybe someone was discussing trade secrets behind the cameraman, and they said, "I get rid of the sound." So we can see them that they're there. Hopefully there's going to be more soon. We have definitely a lot of other entrants out there that maybe next month or let's say first quarter of next year, maybe we'll see a couple others that are also able to demonstrate similar kind of performance. And hopefully there'll be more. I mean, we just don't want to see like a 4-second video. I'd like to see someone doing a lap on a track or something like that where we can actually time the quarter mile or something to get an idea. So we can see that. Okay, so and then I want to just kind of go back to this. This was like one whoops, and I'm going in the wrong direction again here to where I think this here. Okay, so Kyle Morgenstein, who knows quite a bit about RL programming. He's a PhD student, I think, at the University of Austin in Texas, and has done a lot of work, I think, at MIT and others. He put this comment in here, and what I think we want to do is sort of understand it a little bit because I don't think he's necessarily throwing shade here like everyone would think. And so reading it out loud is like, these are just tracking reference motions. So this isn't a measure of the robot's max speed, just whatever was in the retargeted data set. All these demos are the same method, same one Boston Dynamics had earlier this year, and what Unitree, Engine AI, everyone used. So there's part of it is like, did you just take some human motion capture and completely play it back? So it's doing that exactly. Sometimes like, the dance videos and a few other things like that are kind of like that. So it's a question of how much it's improvised. They must have some things on there when they like lose balance, they recover. Then again, a lot of times when we see the Unitree falling down, it seems like they're continuing to play their routine as opposed to like really knowing how to get up. But then there are other cases that say, we'll take the shock and do everything. But so I think what he's saying here is that one way to teach these bots to walk is you just put them into a simulation like we've seen in Isaac Sim, where you put it on down there and just through reinforcement learning over generations and generations, the bot learns to stand up and then to move and do a bunch of things in locomotes. But you need to have a lot of these cost functions in there to give it some sort of reward of what is like a good strategy or a bad strategy to make sure it knows what to do. So you got to put these goals in there, and it's kind of hard to articulate what those goals are. And the problem is these bots may learn to move around, but they will do probably the silly walk. And you'll say, that doesn't look right. We want to change that a little bit. So they're doing something to bias it to look more human-like. Now we can argue whether that is the right strategy. Chris Paxton, I think, was very articulate about that when he said this whole idea that's like, well, wait a minute, robots are not bones and muscles. They're basically motors and aluminum. Uh, so we have to remember that. So their strategy will be different, and that everyone is injecting this human priors in there, which is basically poisoning the well. Uh, but you probably need that in some cases, otherwise it gets lost in these weird minimums and you can't get out of it. So you're trying to do something to get it up there. So there probably is a targeting set. And I think the key point he might be making here is that he may be more or less saying like, "Hey, it's all good and well that you're saying that, that's how fast it is, but do not think it's the max speed. They may have way more headroom in there. It's just that they're kind of limited by the way it's trained. It might be as you really let this thing loose, the things might really be able to go way faster than that, which is maybe frightening. It doesn't surprise me. I'm sure a lot of them will come back and say, oh, yeah, we still have plenty of speed and torque available all over the place that, we could maybe get another 50% or double or something like that. I don't know what it is. Um, so again, it's not a measure of the robot's max speed. And I agree. The speeds I'm not saying that's the max speed. What I'm saying is like what we are seeing is that it can go this fast right now.
To be honest,
Uh,
the skeptic, I don't see this comment even helpful for what you said. That's my opinion. I think it makes sense that they use
well,
this.
I think what it does is everyone that's in the RL community will completely understand this and say that that's a very kind of factual, probably what's going on. The thing is, if you don't understand enough about how the training works, you might think it's coming across a bit snarky, but it's not. I think because so this isn't a measure of robust max speed exactly. So because if they're tracking the references, whatever that reference is like, think about it, the reference was probably one of the guys in the lab, and like the guys in the lab aren't necessarily in the best shape, and maybe there's a couple that are runners. So if they can only run at that speed, that's probably what the motion is going to do. So they need to go out and find an Olympic athlete, but I'm sure they could get the training set to be a little bit faster. Um, or in a way they would be able to do something to get the bots to maybe achieve what you believe to be the top end of
Can I
them.
ask you a question? If Boston Dynamics did this early on, and why Tesla and Figure delayed to show that? If they just to track and reference motion should be.
Oh, yeah. I mean, those are definitely legitimate questions. So, with Tesla, I don't know, to be quite honest, why it's taken so long to see this, because we were seeing Optimus walking really well for the longest time, but it appears that they weren't using RL at the time. That the feeling was it could be done with classical kind of control approach on that, and that there was always this little divide. People will love the upper body. It's just going to be imitation learning because that's where the manipulation is. But everything below, you could probably do it with more classical techniques because you have a limited set of, there's two kinds of manipulation. I think Baird talked about walking as being like, you're manipulating the ground. It's like, yeah, you kind of are, but the number of manipulation tasks that you have for your feet is way different than what you have with your hands. So um, in many ways, it feels like it's a problem you could solve there. And so Tesla was just tuning that, and Optimus looked like it was walking really well, but why they couldn't get the more speed out of it, we could know. And then there was like this long, almost like 4 or 5 month stretch where we weren't hearing anything coming out of the Optimus team, and then suddenly they showed like the new swaggery walk, which was RL. Wasn't any faster than before, but there was like all this excitement of the team. It's like, hey, RL is back, which is sort of like, aha. So there was like this internal debate on which way to do it, and they suddenly had to get on the RL train because Unitary back in January was like showing what they were doing with RL. And then everyone, then Engine AI and a bunch of others are coming on, and suddenly they were having like really impressive gaits, which made everyone think, well, maybe we should give it another try. So it seems like they were doing that. And a month later, of course, we saw that with RL, they were able to get the dancing and all that. And from that, I had felt that, oh, okay, it can finally walk, probably 3 to 5 miles per hour. We should be able to see that because it's definitely get the leg energy, was jumping. It was off the ground. So, I mean, we already were seeing Optimus being able to get both feet off the ground, but technically it wasn't running. It was like dancing in place. Again, why it took so long from here to there, I don't know. It's, and I've been wondering whether there was something else. So remember, there was a suddenly there was turmoil, there was turnover, a lot of different individuals. The this decision to scale was like turned back. They started focusing a lot of energy on V3, and then maybe they just weren't sure if it was worth working on this platform that now was basically deprecated. Um, it seems like they changed the tune a little bit because they started to ramp up producing the V3, the golden bots, or not the V3, the 2.5 golden bots, probably just for internal use, to do other kind of related work that had nothing to do with the hardware. So there's probably a lot of training and other stuff you can do with an existing platform that you will be able to bring over to V3. Um, and what I think is really going on is that your physics simulator has to be really good. If you get your physics simulator working really well, then that means if you have a change of hardware, and you know how to characterize that hardware really well, you can then get the training pretty quick. But what you have to do is find out is it working well. So it's like, well, we don't have V3, but we've got this one here. Let's test it and let's see what our zero shot is on our sim to real. And if we can get zero shot, then we might be confident when the next piece of hardware comes out, it works. Because remember, Humanoid was really excited about the fact that their bot was up and walking in 48 hours. And that means they're saying we were able to simulate it so well that when the hardware came together the first time, we were able to get it to walk. Yeah, it was kind of a very slow walk, but still they got it pretty fast because they're saying we nailed it in the RL. Tesla is probably trying to do the same thing right now, and saying that after they put that on the back burner, to say, oh, maybe we should start doing this a little bit more in prep for the next hardware.
So just to understand all of them, because if what Carl say that all of these companies the same thing, but
Mhm.
what differentiator here is how they model the mechanical part of the actuation. Is that the trick
Yeah.
part that
Oh
miss
yeah.
this?
Yeah. It's very hard. It's it.
But
Yeah.
it seems most of them they have common actuation method. Why?
Yes. 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 And
What was the problem? Is where is the if they all do the same thing as Carl
oh,
said, to
it's like
standard.
you've got to be able to simulate the actuators. I mean, there's so much you've got to simulate in that that gets very complicated. And again, Jim Fan said it back in January that um, you need to do design for simulation, and if you don't, you can kiss RL goodbye. So you've got to. In some ways, he's almost saying, dumb down your mechanical design so we can simulate it better for you because we only know how to do certain things. Um, and that's I, I remember telling robot companies that 40 years ago, and they looked at me and said, "Look, if your simulator can't simulate our hardware, your simulator isn't very good." And we had to like change course and say, "Okay, they're not going to make it easy for us. We're going to have to understand how these mechanisms work and design it that way." And so, the first steps was like a very serial bot. And if you take like a URDF file, which is what's being used in Mujokos and others, and bring them in, you'd be surprised that everyone assumes that their joints are actuated right there. So the elbow joint, they're assuming there's an actuator there, even if it isn't. They're when they come down to like the RSU mechanism, it's not simulated. They just do the cardinal joint because they're trying to figure everything out there and get that working. And then eventually we'll take that and translate it back into it. So what they're having to do is approximate that. They're basically putting pseudo actuators at those joints, and from that trying to approximate what the real one is. And that probably is not the right strategy. And that could potentially be like a limitation of those simulators right now. But Tesla's not using them, right? Because remember, yeah, well, they're not based on NVIDIA, so there's no reason for them to use that stuff, right? It's basically if you're using NVIDIA chips, you're going to be getting the simulation software for it. Tesla is using the FSD chip. They've been having to create physical worlds. So they're writing their own. Yeah.
What simulator figure use and just the use? Do you know what they use
I'm
for the
not sure figures. Well, see, figure is actually very easy to simulate because they're all serial down there. They don't have remote actuation anywhere in there. So I don't know what they're using, but they could be using Isaac Sim and it would work. And that's what the same thing with Unitree is that for the most part they are, except down in their ankle. And you'll see that they changed up the ankle design for age two. And again, there was a researcher who told me that the RSUs are like really hard for the simulators to get right, and that if you can serialize it down there in a way, in a more clever way, then it will be easier for you to get the RL training to work. So part of it is that Tesla had two hands tied behind their back because their actuation strategy was just so hard. I mean, it's like the knee is complicated, the hips are complicated, then you get the ankles down there, and like you need all those joints to be modeled correctly to be able. And so it could be that that was like holding the back for a long time, and they saw everyone else was going there. Everyone else had the advantage because they had a very simple design. Now humanoid kind of impresses me because like their kinematics there was not easy. I mean, we'll see if they can get running. Walking is going to be different than running, but they may have also had to go through there and recognize that like our actuators, you gotta simulate everything in there. Right down to how the reducers are working, potentially what the backlash is going to be, and then the fact that it's remote actuated, you no longer have a linear relationship between the torque output of your motor and what's happening at the joint. So if all those things aren't modeled right, it could make it very, very difficult.
So we don't know what exactly Tesla's using for simulation. Yeah, the
I'm
exact
sure they're
tool.
using it. They're using their own in-house. That absolutely, I'm sure.
Do you know what is it available information what exactly it is like, or it just
No, I haven't seen anything to say what they're using, but my suspicion is they are not using a third party. They are using their own. It's a homebrew. Absolutely. Absolutely. Yeah. Because they may have had that issue. I mean, I remember seeing some of the early Isaac sims that they showed a while back with agility with its bot moving around. And I could see like the back links were not necessarily being simulated, right? It's like, oh, okay, that's like an indication that the simulator is taking a simplified view of the actuation strategy. Yeah, I get this is a hard lesson I learned over 40 years ago, simulating a lot of bots that had backlinks, is that we assumed that the actuators were right at the joint because that's where it was easier to solve the kinematics, but the actuation was starting from somewhere else. And the result is the speed profiles that you were assuming happening around that were false. You were getting the wrong information for that. And not only that, the resultant motion, your TCP, would be radically different. So the start of your move and the end of your move would be absolutely correct. And you'd be doing what's known as a joint space move. But what you need to do when you do simulate the joint space move, you need to simulate an actuator space and not in joint space. Now, if actuator and joint space are the same, you don't have a problem. But when they're different, suddenly you will see you'll have this move and the TCP trajectories, the path could vary by like 100 millimeters. I mean, that is a huge amount. It hits the destination at the right time. And so if you're doing like a spot welding cast, it's like, it's fine. Look, I hit that spot and I've retracted and I've come over to that spot and everything's fine. And you simulate it and you don't hit the fixture. You're all happy with it. And then you download it and suddenly, bam, it's like, what happened? And, and you're looking at this, oh, okay, what's the issue here? And you go and you begin to realize that it's because you didn't actually simulate the mechanism correctly. So if you don't get it right, your trajectories will be completely off. And that's going to be the same thing. And that's just pure kinematic space. Okay. Dynamics is an order of magnitude harder. And so if you're not simulating that the torques are coming from someplace back there as opposed to right there in the jig, you're going to get everything.
that's why we see the shaky behavior that you say
Oh
before.
yeah, yeah. I mean, that's part of it. But the reality is that you simulate it that way is a first order approximation, and that's it. And without getting higher fidelity in there, you're going to have a lot harder problems down the road. Or what that means is that the zero shot's not going to work. It's like there's going to be a lot of post training you have to go through to touch it up to get it to work right.